Okay, in this class we will discuss the stability of steepest descent algorithm. Okay. So you studied that the filter weights at time n plus 1, they are basically obtained from filter weights at time n by adding a correction, which is the mu times negative of the gradient of the mean square error at time n. Okay. So you have W1 is the filter weights at particular time n. So you find the gradient of that is del Jn. So you multiply with minus and with 1 by 2 mu, that is added to this to find the new weights at time n plus 1. Okay. So which was further decomposed as Wn plus 1 is equal to, we got it as Wn plus mu into P minus R Wn. Okay, this is what is the algorithm for steepest descent method. Okay, so you start from any, so in this adaptive filter, D and Y, and this is adaptive algorithm, this is A input. So you start from an initial guess W0, so you update the filter weights at n is equal to 1 W1 using this algorithm. Then W1 at n is equal to 1, the filter weights, you have the vector of filter weights W1, you again find a gradient and update that vector at n is equal to 2, we get W2, W3 and so on. Okay, as per this equation or this equation. So this mu and this R, these are two deciding factors for the stability of this algorithm. Okay. So in order to discuss this stability, we start from a error, you can say weight error vector. Cn. We define vector Cn, which is the difference between Wn and Wo. Now Wo is the minimum mean square error that you get from the Wiener-Hoff equations, that is WR is equal to P. So at any particular time n, you have some filter weights Wn, which does not give you the minimum mean square error. So the difference between Wn and Wo, which is the optimum solution, that gives a filter weight error vector, suppose Cn. Okay. So using these equations, you can modify this equation as Wn plus 1 is equal to Wn plus mu. So in place of P, I can use the Wiener-Hoff solution, that is R W minus R Wn. Or it will become Wn plus mu R Wo minus mu R Wn. So if you subtract Wo from both sides, what will get here? Wn minus Wo plus, or in fact you can take minus from these two terms, you can take minus of mu r as common. Inside you will get Wn minus Wo. Okay. So Wn minus W will be common, so you can write it as I minus mu into R into Wn minus Wo, which is defined as Cn. Okay. I is your identity matrix now. And this in fact will become C of n plus 1. Okay. So it started from a weight error vector, which is the difference between the filter weights at time n and the optimum weights. Okay, so if it is Cn, so Cn plus 1 can be expressed like this. So what we will basically try to do is that we will try to, with the passage of time, as the mean scalar will start minimizing, it means this vector will be, the elements of this vector, they will tend or they will oppose towards 0 because it is the error difference between the optimum weights and the filter weights at particular time n. Okay, so if the error is going to minimize with respect to time, it means as time goes on, the difference between these two vectors is going to be minimized. It will tend approach towards 0. So based on this, we will discuss the stability. Okay, so this Cn plus 1, this is a weight vector at n plus 1 time. It is now I minus mu r into Cn. I minus mu. Now r, see, r can be decomposed as in terms of eigenvalues and eigenvectors, which we have already discussed. Q lambda into QH. Okay, so you can write in place of r as Q lambda QH into Cn, where Q is basically what? It is a eigenvector for this matrix R, and this lambda is the diagonal matrix of eigenvalues. Okay, so this matrix R can be decomposed like this. This is Cn plus 1. Okay, so if you pre-multiply this equation with QH on both sides, C of n plus 1, and there is a property that you know that Q and QH, it becomes Q inverse. Okay, this is a property of the Hermitian matrices that we have discussed when we have studied eigenvalues and eigenvectors. So based on this property, if you multiply this with QH on both sides, pre-multiply this equation, what you will get, QHCn plus 1 will be equal to I minus mu lambda into QH C of n. Okay, so now from this equation we define a new set of coordinates which we define as Vn, which is QH into C of n. So this is Cn, which is the weight error vector, is transformed to a new coordinates V of n. Okay, so if this is V of n, this can be written as V of n plus 1. So I can write it as V of n plus 1 is equal to I minus mu lambda into V of n. Okay, so these new coordinates. Now see, V of n is basically nothing but it is transformed from Cn. So Cn is multiplied with Q of h. So you get V of n. Okay, so the initial error that you have at n is equal to 0, that will be how much? When your n is 0, it will be QH into Cn, and Cn is basically W n in this case is now W0 minus W optimum. Okay, this is Vn, the vector at time n. So basically transformed from Cn, and Cn itself is the error vector, weight error vector. So what is the initial error in the weight error vector is for n is equal to 0, you will get QH into Cn. So Cn is Wn minus Wo, and Wn for n is equal to 0 is W0 minus Wo. So if you assume that okay, at a starting point W0 is 0, the initial vectors are 0, it is minus QH into Wo. Okay. Now from this matrix, or from this equation, what you can get is that you will get a set of equations basically. See, you have this equation which is says that your v of n plus 1 is equal to I minus mu lambda into v of n. It means the vector other vector at n plus 1, this is how you get from time n. Okay, so it is nothing but I is your identity. See, I is your identity matrix. If you have m cross 1 m filter weights, it will be m cross m matrix. So it is identity matrix where all the elements are ones, diagonal elements are ones, and all other elements are zeros. Minus mu times lambda. Now, lambda is the diagonal matrix of your eigenvalues. That is lambda 1, lambda 2 up to lambda m. Okay. So this will be multiplied with your Vm. So if you combine these two equations, so mu will be multiplied with here mu lambda 1, mu lambda 2 up to mu lambda n, and you find the difference, you'll get 1 minus mu lambda 1, then 1 minus mu lambda 2, and so on. These are diagonal elements. So multiplied with Vn. So we can have V0 of n, V1 of n. So this will have m elements, m minus 1 of n. And that is equal to the vector error coefficients at n plus 1. So V0 of n plus 1, V1 of n plus 1 up to Vm minus 1 of n plus 1. Okay. So from this equation, if you relate, so your V0 n plus 1 will be basically equal to 1 minus mu times lambda 1 into V0 n. Isn't it? Similarly, V1 of n plus 1 will be 1 minus mu times lambda 2 into V1 n, and so on. Or you can say, okay, that the kth mode for this vector, kth natural mode, so Vk of n plus 1 in general will be 1 minus mu lambda k into Vk of n for k is equal to 1 to up to n. Okay, so this is a homogeneous difference equation of first order. So if you know the initial conditions, you can find the solution for this. Okay, let us suppose that Vk0, if this is the initial condition for this, what will be the solution for this? See, if I say Vk of 1, it will be 1 minus mu times lambda 1, lambda k into Vk of 0. Then you find Vk of 2, which is equal to 1 minus mu lambda k into Vk of 1. But now since Vk of 1 is this, so if you multiply this with this, you will get 1 minus mu lambda k square into Vk of 0, and so on. So if you know this initial condition for this difference equation, you can write it as that Vk of n will be 1 minus mu lambda k to the power n into Vk of n. So Vk of 0. Okay. Now this will give you the condition for the stability. Okay. Because if Vk0 is the initial condition, that means for any kth mode, if V0 it constitutes the initial error vector weight, so Vkn, the weight error vector at time n, it should diminish as n approaches to infinity. Okay, and that will happen only when this factor 1 minus mu into lambda k, if it is less than 1, or the magnitude of this is less than 1. So the condition will become that okay, minus 1 should be less than 1 minus mu lambda k less than 1 for all values of k. Okay, because it is geometric progression series. Okay, so this common ratio should be less than 1. Or from this alternately what you can say that if this is the condition, it means your lambda or your mu, it should be between 0 and 2 by lambda max, where lambda max is the maximum eigen value. Okay, so lambda k, now it is lambda 1, lambda 2, lambda 3, different eigenvalues for autocorrelation matrix are there. Okay, so for all those cases 1 minus mu k must be limited between minus 1 and 1, or the magnitude of this should be less than 1. So for this to happen, it means mu must be controlled between 0 and 2 by lambda max. See, when mu is 0, its upper limit will be 1. 1 minus mu into lambda k. But mu should not be 0. It should be less than this. If mu is 0, there is no operation basically. Okay. So 1 minus mu k, if mu is very close to 0, this 1 minus mu k, mu times lambda k, this may be very close to 1. But when your mu is now 2 by lambda max, so what you will get? 1 minus mu is 2 by lambda max into lambda k. So if lambda k is equal to lambda max, so in that case it will be 1 minus 2, that is minus 1. Okay. So if your lambda k is 0 or mu is close to 0, so this value is close to 1. When your mu is close to 2 by lambda max, so for lambda max, this is the minimum value. Okay, so it means using this equation will be satisfied. Okay, and if 1 minus mu lambda k is less than 1 for all values of k, so these modes, they will naturally die out with time. Okay, so Vk plus 1, what was it? Vk of n, it was nothing but qh into c of n, Vn. And c of n is now, but it is a difference vector, that is wn minus wo. That is the difference between the filter weights at time n and the optimum weights. So it is just multiplied with qh to transform into any vector Vn. Okay. So as time, if this is less than 1, this factor is less than 1, it means as your n increases, so this will go on decreasing and decreasing. Okay. And as your n will approach to infinity, this will approach to 0. It means after so many iterations, Wn and W0, they will match each other. So as a result, this Cn will become 0 ideally, and Vn also turns to be 0. Okay, so the algorithm will reach to a stable point in that case. Okay, so for the stability of this steepest descent method, this is the condition that mu should be between 0 and 2 by lambda max. So lambda max is the maximum eigenvalue of this autocorrelation matrix.